we've just now seen the terminal characteristics for a capacitor. Next, it would be useful for us to consider, okay, we see now how much charge this thing can store. How much energy does it store? What is the potential energy associated with a capacitor carrying a given amount of charge? So let's try to address that question next. So we have, right, a formula actually that we've been deriving that tells us the total energy that such a device would carry, or any such distribution of charge. Namely, if we want to compute it, we've been told recently that all we have to do is take our double counting correction factor. We then integrate up the potential at every location in space and multiply by the amount of charge at that location. And this makes a lot of sense if you think about it dimensionally. Potential has the same units as voltage, which is energy per charge. So we take the energy per charge at each location, multiply by the charge. That gives us the energy of each little chunk of our system, and then we simply add them up to get the total energy. The only tricky factor is this extra factor of a half that we've now come to understand. Now, in our case, we are talking about two sheets of charge. Here I'll sketch them for us again. A positive sheet up above, a negative sheet down below. And so, because we're talking about sheets of charge, in this particular case, dq is equal to an area patch, dA, right? Each of these surfaces will get divided into little areas dA, and the amount of charge on there will either be plus or minus sigma, depending upon if we're talking about the upper plate or the lower plate. So let's now carry out this integral and see what we have for our total energy. Now, as we perform this integral, notice this sum is over all charges in our system. This sum is actually over, this integral or sum is over both the top plate and the bottom plate. So we're going to actually have two terms. There's going to be an integral over the top of the potential at the top plate times dq, or sigma dA, plus there will be an integral over the bottom plate of the potential that we have at the bottom plate, dq. And now we can substitute in for these various terms. For the top plate, the potential on the top plate is V plus is what we would call it, right? That's the potential of the top plate. That multiplies a positive sigma dA. So I'm saying here that the potential up here is V sub plus, and the potential at this sheet here is V sub minus. So for the top plate, the potential is V plus, and dq is sigma times dA, the plus version of sigma. For the bottom plate, I have my factor of 1/2, and as I integrate on the bottom plate, the potential there is V sub minus, and that then is multiplying the charge on the for each patch on the bottom plate is minus sigma is its charge density times dA. Now we can begin to simplify these. You will notice that the charge density of the plates are uniform, so those can factor out of our integrals. The potential at each plate also is uniform because the electric field is uniform between these plates. So I can factor out the voltage and the potential, and the charge density. So I have a factor of 1/2 that is actually shared for both terms. So let me factor out those halves and open up a parentheses. Then I have V plus times sigma, which I'm pulling out of my integral, and I'm left then with the integral of dA after I've moved both of these terms out. On the minus side, it's going to be the same thing. I already factored out my half. I can factor out my two constant factors. Remember, though, I have a minus sign because it's a negatively charged plate. So that's going to be minus V minus sigma. And once again, I'm just left, when these move out, with the integral of dA. where the first integral of dA is over the top, the second integral is over the bottom. But in either case, when I add up all of these little area patches dA, I'm just going to have the area of my plate. So I can replace this whole integral with A, just like I can replace this whole integral with A. So we're almost there now. You can see I've got 1/2. I've got sigma times A and another factor of sigma times A. So let's factor those out. There's sigma A. And then what's left inside my parentheses that I have to keep inside there because they are different terms, I have, oh, this is an interesting term. I've got V plus minus V minus. That is something that we should recognize. This is a potential difference. This is the difference in potential between the top plate and the minus plate. That is what we call the voltage across the system. That's the voltage going from minus to plus. Remember, voltages are actually potential differences. So let's see, there's a little more we can do here. We're starting to recognize these various combinations. I think you'll also recognize that sigma times A will be the charge density on either plate times its own area. That is going to be the charge that has accumulated on either of the plates. So we now actually have our final result. Let me actually write it down below here so we can write it as a nice equation that we could then put a box around. Here, if we just slide this up a little bit, what we've been computing is the total potential energy of the capacitor, the energy stored in the capacitor. And what we're seeing here from what we have up above is that it's 1/2 Q times the voltage on the capacitor from the minus to the positive side. Terrific. So now, if we happen to know the charge and the voltage on our capacitor, we can form this product, and that is the total energy stored. Now, if you think about it, this is the product of our two terminal characteristics, the charge that's flowed in and the voltage across the device. This should remind you a little bit of something like I, which was the associated with the charge flowing through a resistor, right, times V. Remember, I times V, that was the formula for power in a resistor. Here, we have a formula for energy, which has Q times V. And just like in the resistor case, where we had 3 independent formulas that we could use, we should be able to generate a similar set of formulas for the capacitor. So, for instance, we can substitute in what we know. We know, in fact, that Q on the capacitor, the amount of charge stored, is the capacitance times the terminal voltage from the minus to the plus. So that's one substitution that we could make. If we did that, we would find then that the total energy is 1/2, and then we're going to have CV times another V when we substitute in here. So 1/2 C times 2 factors of V is 1/2 CV squared. That's one famous formula for the energy stored in a capacitor. This one's most convenient if you happen to know the voltage. We can also do it in terms of charge. We could substitute in for V. If Q equals C times the voltage, then the voltage we know we can relate to the charge. If I solve Q equals CV for voltage, I would get Q divided by C. So I could say voltage is the charge on those plates divided by the capacitance. And if I substitute this in for voltage, I'll have 1/2 Q times, and when I substitute in this way, I'll have another Q on top. So it would be Q squared then divided by C. So that's my other formula. It can also be written as 1/2 Q squared divided by C. So we have now our 3 standard famous formulas for the energy stored in a capacitor, this new type of electrical energy storage device.